All right, so are you ready to dive into this? I'm pretty excited about this one.
Yeah, let's do it.
Today we are tackling simple harmonic motion, or SHM. And, I was looking over the webpage that you sent me about this interactive physics simulation, and it looks awesome.
Yeah.
I think it's going to be a really cool way to really visualize how this all works.
Yeah, and they give a good example too. I like how they get into the specifics of, they give you a spring constant and a mass,
Yeah.
and then they challenge you to think about when the velocity and acceleration are working together versus when they're kind of fighting each other during the oscillation.
Right, and, I'm thinking about this example that they give with a spring constant of 9 newtons per meter and then a mass of 1 kilogram.
Yes.
Like, not 9 newtons per meter sounds kind of, you're technical, but basically it just tells us how stiff the spring is.
Yeah.
Right? So like the really high spring constant means it's a super stiff spring.
Right.
So, you can think of it like comparing a rubber band versus like a heavy dang metal spring.
Yeah.
And then the 1 kilogram mass. I was thinking like, okay, that's about the weight of a standard bag of sugar. So you kind of have a visual in your mind.
Right.
But then they hit you with this question like, okay, when are the velocity and acceleration in the same direction versus opposite directions? I was like, wait a minute. Shouldn't they always be kind of working together?
Well, that's where understanding the restoring force is really key.
Okay.
So think about it. When you pull a spring, it wants to snap back to its original position, right?
Right.
That's the restoring force. And in simple harmonic motion, that force is always trying to bring the system back to that equilibrium point.
Yeah.
That sweet spot where the spring is neither stretched nor compressed.
Okay, that makes sense. But how does that explain why velocity and acceleration are sometimes, on the same team and sometimes they're not?
So let me ask you this. Have you ever been on a swing?
Yeah, of course. Who hasn't been on a swing?
All right, so think about when you're at the highest point of that swing.
Okay.
You've momentarily stopped, right? Your velocity is 0, but gravity's pulling you back down toward the center. So your acceleration is at its maximum and pointing downwards.
Gotcha.
Now, as you swing down, you gain speed. So your velocity is increasing in the downward direction, and you're still accelerating downwards because of gravity.
Okay.
So in that part of the swing, velocity and acceleration are both pointing in the same direction.
They're working together. They're like a team.
Exactly.
Okay, so then as you go through that bottom point and then start swinging back up, your velocity is at its max right at the bottom.
Right.
But then you start slowing down as you go up.
Yeah.
So it's almost like your acceleration is working against you at that point.
Exactly.
Yeah.
And that pattern just repeats with every swing.
Okay.
Now let's map that same idea onto our spring and mass system.
Okay.
So when the mass is farthest from that equilibrium point, its velocity is 0, just like you at the top of your swing.
Yeah.
But that spring is pulling it back towards the center. That's that restoring force, giving it maximum acceleration. Then as the mass moves toward the equilibrium, it picks up speed. So both velocity and acceleration are pointing toward the center.
Okay, so they're working together again, just like on the downswing.
Exactly. But then things get interesting as the mass passes through that equilibrium point, because even though it's still moving toward the other end, it starts slowing down.
Right, because the spring's pulling it back in the other direction.
Exactly. So its velocity is heading one way, but the restoring force is trying to pull it back to the center, meaning the acceleration is now in the opposite direction.
Oh, okay. I think I'm starting to see it now.
Good. Now, to answer the website's question about when they're aligned and when they're opposite, they talk about dividing the oscillation into quarters, like a pie chart.
Okay.
So from 0 to 1/4 of the period.
Okay, hold on. Wait, now, period. What does that refer?
Oh, yeah, good point. So the period is just the time it takes for one full back and forth motion.
Oh, okay, got it.
So from the start of the oscillation to 1/4 of the way through, the directions are opposite. Then from 1/4 to halfway through, they're aligned. And then it flips again from half to 3/4, and then again from 3/4 back to the starting point.
So it's like this constant back and forth between aligned and opposite throughout the whole cycle.
Exactly. But the key here isn't just to memorize these, time frames. It's to really understand why this flip-flop is happening.
Right, and it all comes back to that restoring force and whether the mass is moving toward or away from that equilibrium point.
Exactly.
Okay. Yeah, that's making a lot more sense now.
And that's where the website's simulation comes in.
Okay.
They have this really cool interactive model where you can actually change the starting position of the mass or, how fast it's initially moving. And it lets you really see how those changes affect the entire oscillation.
So you can actually visualize what we're talking about.
Exactly. It helps solidify these concepts. And I think you even have the link in the show notes, right?
Absolutely. Yeah, I highly recommend checking it out after this deep dive. It's actually really cool. You can access it on your computer, tablet, even your phone.
Wow.
It's like having a little physics lab in your pocket.
It's pretty amazing what they can do with technology these days.
I know, right? So we've covered a lot of ground already. We've talked about, the restoring force, the equilibrium point, and even how a swing analogy can help us understand this whole velocity and acceleration dance.
Yeah.
But I think there's so much more to uncover here.
Yeah.
What do you think? Are you ready to keep going?
Absolutely. Let's dive even deeper.
Okay, great. I'm excited to see where this goes.
You know what's really fascinating about this whole thing is it's not just about springs and swings, right?
Oh yeah, definitely. Like, where else do we see this kind of thing in action?
I mean, you see these principles of simple harmonic motion everywhere you look. You think about pendulums, like those weights swinging back and forth.
Right.
Or how a guitar string vibrates.
Right.
Even the way tall buildings sway slightly in the wind.
Wow. Yeah, you're right. It's like once you understand these fundamental principles, it's like you're seeing the world in a whole new light.
Exactly. And the biggest takeaway here isn't just being able to, recite when velocity and acceleration are in the same direction or opposite directions during that oscillation. It's about understanding why that restoring force creates this kind of push and pull between those two variables.
Yeah, it's like getting to the heart of it, not just memorizing facts.
Right. And once you grasp that, you can apply these concepts to any system that oscillates back and forth, even if it seems super complicated at first.
I mean, this is why I love physics.
Yeah.
There's this underlying order and elegance to the universe that you might not even realize is there.
It's true.
Like, even in the chaos of everyday life,
Yeah.
these fundamental principles are kind of running the show behind the scenes.
Yeah. And what I really appreciate about this website is that they do such a good job of breaking these complex ideas down into bite-sized pieces that anyone can understand, even if you don't have a background in physics.
Yeah, it's really approachable.
Right. They don't just throw a bunch of equations at you and technical jargon at you. They use clear explanations and real-world examples and visuals to guide you through the process.
It's like they're holding your hand as you learn, which can be really helpful when you're tackling something new,
Yeah.
especially in physics, which can sometimes feel a little intimidating.
Yeah, it can be a bit daunting.
But this website makes it fun and accessible for everyone, which is awesome.
They've really struck a good balance between being thorough, but also keeping it engaging.
Yeah.
And then the interactive simulations take it a step further by allowing you to actually experiment and test out different scenarios yourself.
Right. So it's not just reading about it. It's like you're actually doing it.
Exactly. And that's what helps solidify your understanding. It's active learning at its best.
Yeah, definitely. So to everyone listening, if you're looking for a way to learn about simple harmonic motion that's actually enjoyable, I mean, this website is definitely worth checking out.
Absolutely.
And as always, the link is in the show notes.
And don't just skim through it. Really take the time to dive in and play around with those simulations and see if you can answer those thought-provoking questions they pose.
Yeah, that's a great point.
You might even want to try applying what you've learned to other oscillating systems you come across in your daily life.
That's such a good idea because, like we've been talking about, SHM is everywhere, right?
It's true.
It's in pendulums, guitar strings, even buildings swaying in the wind.
Yeah.
But what about things like a vibrating drum head?
Oh, yeah.
Or the oscillations of a bridge? I mean, could you apply these same principles to analyze those systems?
Absolutely. And that's where things get really exciting. Once you understand these core concepts of SHM, you start seeing these connections and patterns that you never noticed before.
It's like the world opens up to you in a whole new way.
It really does. And the possibilities are practically endless. The more systems you analyze through this lens of SHM, the more you'll deepen your grasp of these fundamental principles and how they govern the universe.
So it's not just about learning some formulas or equations. It's about gaining a whole new perspective, a new way of thinking about the world around you.
It's about expanding your understanding and seeing the world with fresh eyes.
Exactly. So what are some other real-world examples of SHM that people might encounter in their daily lives? I mean, we've talked about the obvious ones like swings and pendulums, but I bet there are some less obvious examples that we might not even think about.
Oh, definitely. One that comes to mind is the way your car bounces up and down on its suspension system when you hit a bump in the road.
Oh, yeah.
That's actually SHM in action.
Really?
The springs in your suspension system act as the restoring force trying to bring your car back to its equilibrium position after that bump disrupts it.
Wow, I never even thought about that. But it makes total sense.
Yeah.
So it's like our cars are basically giant masses on springs.
Yeah.
Just like the simple system we saw on the website simulation.
Exactly. And the principles are the same. The stiffer the springs in your suspension, the faster your car will oscillate back to its equilibrium position. It's like having a higher spring constant, just like in the example we discussed earlier. And the heavier your car is, the slower it will oscillate, just like increasing the mass in the simulation.
That's so cool. It's amazing how these same principles apply to such a wide range of systems, from tiny atoms vibrating to massive buildings swaying in the wind.
It really highlights the elegance and universality of physics, and it's a reminder that even though the world can seem incredibly complex, there are these underlying principles that govern everything, and understanding them gives us this incredible power to analyze and predict how things will behave.
It's like unlocking a secret code to the universe.
Exactly.
And the more we understand these principles, the more we can appreciate the beauty and complexity of the world around us.
Yeah.
I feel like we could talk about this all day, but I think we're getting close to wrapping up this deep dive.
Yeah, you're right. We have covered a lot of ground. But before we wrap up, I have one final thought-provoking question for you and for all our listeners out there.
Okay.
We've talked about swings and springs and pendulums, even cars. But what about other systems that you encounter out in the world? Could you apply these same principles of simple harmonic motion to analyze them?
That's a good question to think about. I mean, we briefly mentioned things like drum heads and bridges. But now I'm thinking even bigger. What about something like the tides rising and falling? Or maybe how populations of predators and prey cycle up and down over time? Is there a way to see simple harmonic motion at play there too?
Exactly. It's all about recognizing those patterns of oscillation, that back and forth motion around a central point. And even if those systems themselves are more complex than, a simple spring and mass, those core principles that we've been talking about, that interplay between displacement, velocity, and acceleration, and that all-important restoring force can still provide a framework for understanding how these systems behave.
I love that. So it's not just about memorizing formulas or being able to solve physics problems on a test. It's about having this new lens through which to view the world, a new way to approach analyzing patterns and cycles. It's like simple harmonic motion is this hidden language that's operating all around us. And once you start to understand it, you can see it everywhere.
It really is. And the beauty of it is that there's always more to discover, more systems to explore, more connections to make. This deep dive was just a starting point, a taste of this fascinating world of oscillations. But now it's up to you and our listeners to keep that curiosity going.
So if you're out walking around, you notice something moving back and forth.
Right.
Maybe it's a tree branch swaying in the wind or a metronome ticking back and forth.
Right.
Take a moment to think about those forces at play. Is there a restoring force trying to bring that object back to the kind of equilibrium? Can you visualize how the velocity and acceleration might be changing throughout that cycle?
And remember, you don't need to be a physics expert to appreciate this stuff. It's all about being curious and asking questions and exploring the world around you with open eyes. Who knows? Maybe you'll even discover some new examples of SHM that we haven't even thought of yet.
That's the best part. There's always more to learn, more to discover. So as we wrap up this deep dive, that's the message I hope everyone takes away. Keep exploring, keep asking questions, and never stop being curious about the world around you. And hey, if you stumble across any mind-blowing examples of SHM out there in the wild, be sure to let us know. We'd love to hear about them.
Absolutely. The journey of discovery never truly ends. And with a little bit of curiosity and a willingness to explore, who knows what amazing insights you might uncover.
Well, that's a wrap for today's deep dive into the world of simple harmonic motion. We hope you enjoyed the ride, and we'll catch you next time for another fascinating exploration of the universe and beyond. Keep those brains buzzing.